another example of being able to compute the volume revolved about an axis. This time we have the function 2 minus x squared in quadrant 1 rotated about the x-axis. All right, so just kind of looking at what that kind of looks like. This is our function 2 minus x squared, all right? Or actually, if I erase that, it's going to start at 2, and then it's going to go down here, all right? And this is the area that we're revolving, all right? And remember, when we revolve it about the axis, all right, we're getting something like this, okay? So it's kind of going to look like a funnel or something of that nature where the end is going to be closed off, all right? So, and of course, we'll be graph this in Wolfram Alpha to look a little bit better. One thing it does tell us also is that it's in quadrant 1. And what we're going to have to do is we're going to have to find the limits of integration. Now, clearly, we know that x equals 0. So right here, this is the point 0, 2. All right, so that's easy enough, right? But what's not so easy is maybe identifying this point, okay? So this is our a is equal to 0, and then b is equal to where it intersects the axis. So 2 minus x squared is going to be 0, 2 equals x squared. And now technically it's plus or minus square root of 2 equals x, but we really only want the positive root. Okay, remember when if we were to look into quadrant number 2, there would be more of the parabola, but we don't want that. We just want what's in quadrant number 1. Okay, so our limits of integration are going to go from 0 to square root of 2. Right? And so our integral, remember, for our volume, it's pi integral a to b f of x squared dx, right? And so what we're going to do is we're going to take our pi from 0 to square root of 2. We have the function 2 minus x squared dx. Right? Now remember, when we square this out, we're not going to get 4 plus x to the 4th. Okay. Remember, when you square something, you have to write it next to itself twice. Okay. So this is 2 minus x squared, and then 2 minus x squared. All right. And then we're going to FOIL that out. Okay. Ultimately, when we FOIL it out, it's going to end up being 4 minus 4x squared plus x to the 4th. Okay. So that's going to be our integral that we're worried about. And so what we end up with is going to be pi integral 0 to square root of 2. Now we get 4 minus 4x squared plus x to the 4th dx. All right, just by FOILing all that out. Okay, if you don't trust me, FOIL it out so you can see for yourself. Integration, really easy. All right, this is going to be 4x minus 4/3 x cubed plus 1/5 x to the 5th from 0 to square root of 2. Now, unfortunately, the square root of 2 is going to present a bit of a problem for us, but not too much. All right, and I'll show you the way to algebraically simplify this so you can actually get one unified answer. 0 is really nice because when we substitute 0 in, it doesn't really matter. Okay, it's going to wipe it out. Okay, so this is going to be technically pi 4 roots of 2. That's not too bad. 4/3 square root of 2 cubed. And I put the cube underneath the radical because I'm going to show you some algebra tricks with the radicals, right? Plus, similarly, 1/5 square root of 2 to the 5th power. And technically, there's a minus 0 in there because when you plug 0 in, everything goes away. All right, now, square root of 2 to the 3rd, we could think of that as the square root of 2 squared times the square root of 2, which actually turns into 2 roots of 2, okay? So that's what we're going to do is we're just going to simplify these radicals. Square root of 2 to the 5th is equal to square root 2 to the 4th times square root of 2. We know that square root of 2 to the 4th is the square root of 16, which is going to be 4 roots of 2. And so we're just going to substitute those values back in for this square root of 2 cubed, square root of 2 to the 5th. And so we're going to get pi, and we're just bringing this down at this point. Okay, so now we're just going from what we had before. So this is going to be still 4 roots of 2 minus 4 times, or 4/3, excuse me, times 2 roots of 2. And then finally, plus 1/5 times 4 roots of 2. All right. And so now we can simplify a little bit more. So this is going to be 4 roots of 2 minus 8/3 roots of 2 plus 4/5 roots of 2. All right, we're going to get a common denominator of 15. And so now you can see it gets a little bit ugly, but that's okay. We'll be able to do it nicely. So pi, we're going to get 60 roots of 2 over 15. All right, since that's 60 over 15 is 4. Minus, we're going to multiply the numerator by 5. So that's going to be 40 roots of 2 over 15. And then we're going to multiply by 3. So 12 roots of 2 over 15. And so ultimately, we'll get 40. 60 minus 40 is 20. 20 and 12 is 32. So we should wind up with 32 pi roots of 2 over 15 as our singular answer. Okay. All right. So, and then just making sure that you guys simplify this, because when you enter your answers, you are going to have to make sure that you simplify completely, such as this. A way to verify that you've done all of your algebra correctly is to go into Wolfram Alpha, and we could actually just type in the original function as well, all right, and see what happens. All right, so now when we type this in, we're going to type in a little bit more than what we did last time to check our answer. So we are going to rotate y equals 2 minus x squared over 0 comma square root 2. And that's going to be about y equals 0. Okay. Now we could say in quadrant 1. Okay. So we wouldn't even, another way to do this is just kind of omit that. And we could just say in quadrant 1. But this is just kind of implicitly says that it's in quadrant 1 anyway. Okay. So let's see what we get out of this. And hopefully I don't have to make this video again. All right. So that's the area of the surface we don't care about. Volume of the solid. 32 roots of 2 pi over 15. Okay, and if you guys recall, that is precisely what we got. I just reordered it a little bit differently than Wolfram did. So Wolfram's smart, but doesn't necessarily put it in the same order that we do because it can't predict it. Okay, and then also what it does, remember this was our curve. Okay, so if we go all the way back to the original problem and the diagram of that. So remember we kind of rotated it here. And then we just said that we're going to take this and we're kind of going to get like this sort of diagram. Okay, it's going to be filled in completely. All right, so we just took the area. And if we look back at what Wolfram Alpha is, it says exactly that. Okay, so it sort of looks like a satellite dish or like a cone or some like a really flattened out cone or something like that. Okay, all right, so those are another example of being able to work with these volumes of revolution. All right, so next video, we're going to take a look at another one of higher difficulty.